Once we performed an ANOVA and we've got a significant result, we need to perform additional tests, we call these post-hoc tests, in order to determine where the significant differences are within our groups, or between our groups, I should say. So to do that, in Excel, we're going to do this. I've already recreated my ANOVA, and what I've done this time, just so it's a bit more consistent with the text on the book, is I've put it into a new sheet. I've relabeled the sheets, so I've called this sheet tests, and I've called my wide table wide. I've labeled it wide. Okay. So I've also created a couple of additional tables underneath my summary and ANOVA table. These tables have come from my data analysis one-way ANOVA. And I've called the first table post-hoc tests, and I've called the second table alpha. So before I discuss what I'm going to do here, I need to create all the possible pairings between those groups. So I've just compared each of those groups together and written that down. I hope you'll agree there are 6 ways you can do that. So I can do 0 versus 1.5, 0 versus 2, 0 versus 2.5, and then 1.5 versus 2, 1.5 versus 2.5, and 2 versus 2.5. Okay. And what I'm going to do now is I'm going to perform a t-test. Now, a t-test is a test that determines whether there is a significant difference in the mean of 2 groups. So each one of these groups, every time I apply a t-test, I'm essentially testing the null hypothesis. There is no significant difference in the mean values of these 2 groups. Okay, and for, again, just like the ANOVA, I can compare that to some alpha threshold, in this case 0.05 again. And if it's less than that, then I reject each of those hypotheses. Okay, so I'm going to perform a t-test in Excel for each of these groupings, these pairwise comparisons, and determine a p-value. Now, in Excel, it will look like this. I'm going to type equals into this column here. I'm going to type t-test, surprise, surprise, and that's going to take a number of variables here. So it's actually going to take 4 things. The first is going to be all of the data from my first group. The second is going to be my data from my second group, and we'll worry about what these last 2 are, tails and type are, in a second. I'll give you a bit more information here. So the first thing I'm going to do is once I've typed equals t-test, open up my first bracket, I'm going to head on over to my wide sheet, and I'm going to select all of the data except the head. I'm not going to include the headings this time. I'm going to do all of the data in my first group, my control group, 0. I'm not going to include the blank or the grand total. Okay, and then I'm going to click comma. I'm going to hit comma, right? Before I move on, I'm also going to put a $sign between the column label and the row number. Okay, and the reason for that will become obvious very shortly. I also want to put in the values for the second group that I'm comparing. So that's the 1.5, so I'm going to select all of those. And I'm going, again, to put the $signs here. Okay, so 2 more things. So another comma. And I'm going to put in a value here for this tails variable. Now, you can put a number of values in here. Actually, you can only put one. You can only put 1 or 2 in here. Now, I'm going to put a 2, and you can see if I type that, it gives me a couple of options here. And by selecting 2, I'm telling my t-test that I want to apply this to a 2-tailed distribution. Now, that doesn't really mean anything like that. In this context, it means that I don't know the specific direction of the change between the groups. Okay, so I know that what's happening here is it looks like the average lengths of the embryos are decreasing with alcohol concentration. But they could equally increase, right, for whatever reason. So because I don't know for certain the direction of that change, I have to select two-tailed. Okay, so this is a two-tailed t-test. The last parameter here is called type, and there are three potential values you can take: 1, 2, or 3. I am going to use 2, and you can see here once I type that, it gives you these options. The 1 would be for a paired t-test. Now I should only be using paired t-tests on groups where the members of each of those groups, or the measurements in each of those groups, belong to the same thing. Okay, so for example, the classic example is looking at test scores for students. So if I gave you and your peers 2 separate tests, and I wanted to know whether there was a significant difference in the mean scores between your first test and the second test, because the individuals in each of those groups are the same, I would use a pair t-test. Now in this case, for these zebrafish, it's not the same. Okay, the zebrafish are only in one group at a time. You can't treat them twice. So we're actually going to use a what we call a 2-sample. It's also called an independent t-test sometime. And there's a very subtle distinction between 2 and 3. 2 is for the assumption of equal variance. So remember, that was an assumption of the ANOVA as well, is that the variances between each of those groups should be very roughly the same. Now that's true in this case, I know, because I created the data set. In some cases, that's just simply not true. And there is another alternative we can use, that's called 3, for a 2-sample t-test where we know that the variance is unequal. It's also called a Welsh test. I guess that's after Mr. Welsh. And we'll encounter that again later when we start doing t-tests in R. So for now, I'm going to close that bracket and I'm going to hit enter. It's going to take me back to my original test sheet. And you can see I've got a p-value of 0.69. So initially, if I was using a threshold of 0.05 to determine whether that result was significant, because it's so much higher, 0.69 is much higher than 0.05, I would accept my null hypothesis. In other words, there is no difference in the mean values between those two groups, 0 and 1.5. So I'm now going to proceed to do the same for the rest of my pairwise comparisons. Now, let's just drag that down. This is the fiddly bit. So I think what I'm going to do here is I'm going to do a couple of these, and then I'm going to skip ahead. If you look at all I've done there is copy that cell down and into the one below it. It's the same, and it's the same because I put those dollar signs in, okay? And I haven't changed the column labels for each of those. So what I would need to do now is, rather than compare column B and C, I want to compare B and D. You can see here, this time I want to do B and D, 0 and 2% alcohol. So to do that, I'm gonna keep the B the same, but I'm gonna update the D. And I'm not gonna change anything else. There you go, that'll give me another value. This time it looks like it is below 0.05. So it looks like there is a significant difference between the mean values of embryo lengths in the control group, 0% alcohol, and the 2% alcohol group. Right, I'm now going to proceed to do that for all of these. So this is going to be between B and E. Okay, and so on and so forth. I'm going to skip ahead here and let you do this. Okay, I have done that, and you can see here that if I was applying my threshold of 0.05, then I could say there is a significant difference when comparing the groups 0 and 2, 0 and 2.5, 1.5 versus 2, 1.5 versus 2.5, and 2 versus 2.5 is not significant. Okay, it's above the threshold. That's if the alpha was 0.05. Now, I have to be extremely careful here. I cannot use any longer that threshold of 0.05. And there is a very good reason for that. It's because if I have multiple tests that require multiple hypotheses, I am increasing the probability that I'm going to return a false positive result. Okay, so there is a probability that I could do a t-test and it would tell me it was significant even though it wasn't. Okay, and the more tests I do, the more likely that is to occur. So the way I get around that is by changing the alpha that I'm using. We call that a Bonferroni corrected alpha level. Okay, after Mr. Bonferroni, I'm sure. And to calculate the new threshold that I should be using for my t-tests, it's really, really simple. I'm going to take that 0.05 that I've already used for the ANOVA, and I'm going to divide it by the number of hypotheses, the new hypotheses I have. In that case, it's 6, one for each group. So I'm going to do equals 0.05 divided by 6. And I now got this new Bonferroni corrected alpha level that I should be using to determine whether the p-value for my t-tests lead to a significant result. Okay, so just a bit of Excel here. I'm going to make an if statement in this column, and I'm going to say if my p-value is less than my Bonferroni corrected alpha, and I'm going to put in a dollar sign here and a dollar sign here. Okay, then I'm going to put a comma there, and then it is significant, so I'm going to hit yes, comma, otherwise no. Okay, so that's just a simple if statement there in Excel. So the first one, no, and if I can copy those down, it'll tell me when and when they're not. There you go. Right, so I have performed my post-hoc tests. So in addition to my conclusion that there is a significant difference between the variation in the means of each of these groups, I can also say that the significant differences occur for these groups 0 versus 2, 0 versus 2.5, 1 versus 2.5, and a 1 versus 2 as well. Okay, and if I'm writing this up, I should quote those values too. Okay, that is the end of this week. You learned a lot, I hope, and we will return to ANOVA and post-hoc testing in a couple of weeks' time when we do exactly the same thing, but we do it in R. Okay, so exciting. You're going to love it. Right, thanks for listening.